Welcome everyone to today's Explainer. I am absolutely thrilled to guide you through Chapter 18, where we'll be focusing on Service-Oriented Architecture, or SOA, and web services. As we progress through our software engineering syllabus, we're really moving away from those old-school, monolithic, standalone applications. Modern software engineering relies heavily on distributed systems. So understanding exactly how independent programs communicate and share data across the globe is absolutely crucial for your future careers. Let's get into it. All right, here's our roadmap for today. We'll quickly cover 1. An introduction to web services, 2. Services versus components, 3. The in-car example, 4. SOA defined, 5. The standard stack, and finally, 6. A quick exam recap to make sure you're ready for test day. Okay, let's dive right into this. Section 1, Introduction to Web Services, the paradigm shift. To really understand why web services were even invented in the first place, we have to look back at how the internet used to function in its early days. So I want you to think about this question. What was the fundamental problem with the early web? Well, in the 1990s, the web completely revolutionized information exchange. But there was a major catch. Early web browsers were designed strictly for human readers. If you were a person sitting at a desk, you could easily read a web page, but direct, programmatic communication, that was practically impossible. A program couldn't just automatically query a bunch of catalogs from different suppliers to find the best price. The information was entirely locked behind interfaces meant for human eyes only. And that is exactly the paradigm shift that web services introduced. They solved this massive limitation by enabling programs to dynamically exchange data across the internet. They provided a standard representation for computational or information resources that could be used directly by other programs. So instead of a human clicking a button on a browser, a program can now send a request over the internet and receive structured data right back. This meant systems could finally talk directly to other systems, which opened the door for massive automated data exchange. It was a real game changer. Moving on to Section 2, Services versus Software Components, a crucial distinction. Okay. I want you to pay very close attention right here. This is a crucial distinction and, honestly, a classic exam trap that you absolutely must recognize. Let's compare the two concepts clearly. In component-based software engineering, or CBSE, a software component typically has a provides interface and a requires interface. It tells you what functionality it provides, sure, but it also explicitly defines what external components it requires to function properly. A web service, on the other hand, it has a provides interface only. Why is that? Because a fundamental rule of a web service is that it must be completely independent and loosely coupled. It should always operate in the exact same way, regardless of its execution environment. It doesn't rely on external components that might have unpredictable functional or non-functional behavior. It literally just provides its functionality to whoever requests it. Section 3, Real-World Application, the in-car information system. To really cement this abstract theory in your minds, let's ground it in a practical, real-world application from our textbook. The in-car information system is a brilliant example of how service-oriented systems actually operate in the wild. If we trace the flow here, we have an in-car software system communicating with external services. The car has a GPS receiver to pinpoint its position and a radio to deliver audio to the driver. As the car drives, its transmitter sends out its coordinates. Notice how it interacts with a service discovery module and a mobile info service. It actually uses these to pull in weather, traffic, and facilities information, and then, this is the cool part, it even passes that data through a translator module before playing it out loud on the radio. Let's break down the chronological steps of what's happening in that dynamic discovery process. First, the car drives into a totally new city and requests information. Second, instead of relying on some hard-coded weather app for a specific town, it discovers a local weather service based purely on its current GPS coordinates. Third, it dynamically binds to that local service on the spot. And fourth, it translates the information into the driver's preferred language, which means the car can cross international borders completely seamlessly. We call this opportunistic construction. The software decides exactly which service provider to use on the fly, depending entirely on what is available at that specific time and place. All right, Section 4, Service-Oriented Architecture, or SOA, the mechanics. Now that we've seen opportunistic construction in action, let's define the actual architecture that makes these dynamic web services possible. Sticking to our academic rule of defining a concept before explaining it, let's look at the formal definition. Service-oriented architecture, or SOA, is an architectural style based on executable services with published interfaces. In simple terms, this means that applications are built by choosing and combining these independent executable services at runtime. The exact same service might actually be available from several different providers, and the application gets to make a runtime decision about which one is most appropriate to use in that moment. Now, what is really interesting about this slide is how the three main actors interact to make all of this possible. You can clearly see the flow of finding, publishing, and binding between the service registry, the service requester, and the service provider. Let's detail the exact roles of these three actors, because they are a big deal. First, the service provider. They design, implement, and publish the service. Second, and please definitely flag the specific role for your exam, is the service registry. Think of the registry as a giant searchable catalog where all these published services are listed along with their interfaces. Finally, the service requester is the application that queries the registry, discovers the specification of the service it needs, and then binds to it. Without that service registry acting as the middleman, the opportunistic construction we just saw in the car example simply wouldn't be possible. Section 5, Web Service Standards, the XML stack. So for disparate programs written by totally different companies in entirely different languages, to communicate flawlessly, we need a heavily standards-driven XML-based foundation. Slowly walking through this standards stack, we see that because SOA is built on these internationally agreed standards, it avoids all those messy incompatibilities of proprietary technologies. Down at the very base, everything relies on XML technologies to structure the data. Moving up the stack, we see layers for support, process, service definition, messaging, and transport. Now, I know it looks like an absolute alphabet soup right now, but these heavy acronyms are exactly what ensure reliable, standardized program behavior across the globe. Let's isolate the absolute must-know acronyms for you. First up in that alphabet soup is SOAP. SOAP is the messaging standard. It dictates exactly how services talk to one another and exchange information. So when one service sends a request to another, that message is strictly formatted according to the SOAP standard. This ensures the receiving service knows exactly how to parse the XML, carry out its computation, and send a standard, predictable reply back. Next, we have WSDL, which stands for Web Service Description Language. WSDL defines the service interface itself. To make this really easy to digest and remember, just use the what, how, and where framework from your textbook. A WSDL document specifies what the service does by defining its operations, how it communicates by mapping the interface to a messaging protocol like SOAP, and where to find it by providing the specific internet location or endpoint of the service. And finally, to complete our standard trio, we have UDDI. UDDI is the discovery standard. It essentially acted as a sort of global phone book for services, allowing requesters to look up providers in the registry. It's really important to note for historical context that while it completely paved the way for service discovery, UDDI is actually largely obsolete in modern systems today. All right, bringing it home with Section 6, exam summary and next steps. If you remember one thing for the test, let it be this final review section. We have covered a lot of ground today, and I want to ensure you are laser-focused on the highest value concepts. So, the crucial points you must be able to explain are, first, contrast a component with a service. Remember that a component has a requires interface, while a service is completely independent and is provides only. Second, you absolutely must be able to explain the role of the service registry as the searchable catalog that enables service discovery. Third, define SOAP as the messaging standard that allows services to talk. And fourth, recognize WSDL as the web service description language that defines the interfaces what, how, and where. Memorize these definitions, understand how they fit together like a giant puzzle to create a service-oriented architecture, and you will do exceptionally well. We've spent this entire explainer looking at the heavy WS star standards that built the foundation of SOA. But I want to leave you with this provocative thought to ponder. While these heavy XML standards built SOA and ensured incredibly reliable communication, are they the only way modern developers build services today? Well, as you'll see in our next lecture covering Section 18.2, the industry is increasingly shifting towards simpler, more lightweight RESTful services to minimize processing overhead. But we will save that fascinating evolution for our next session. Thank you so much for joining me. Keep reviewing those definitions, and happy studying.